Now, today we will be extending what we were doing in the previous class. I give you a recap. We dropped an object from a tall building, and then we observed that how distance is changing, how velocity or speed changes, how acceleration changes, how kinetic energy and potential energies change with respect to time. And then we threw an object upwards and then caught it back on the same point again. This was the graph for how distance traveled by the stone changes, the graph of displacement of the object from the ground, how speed changes, how velocity changes, and how acceleration changes. I hope you remember this. Now, today we are extending this thing. There is a person standing on a very tall building, and that person throws something upwards, which goes up, and then when it falls back, the person does not catch it and lets it fall to the ground. Okay. So an object is thrown up, and then instead of catching it back at the same height, we let the object fall down to the ground. The title of this kind of example is an object thrown upwards from the top of tall building. No air. There's still no air involved over here. Just 1 second. Let me. Now, what will be happening to different things? Speed decreases with constant deceleration. Of 9.81 meter per second square. Then at max height, speed becomes 0 momentarily. Object falls back with uniform acceleration downwards. Now, how can we draw this information on graph? Like what graphs we need to draw? First, we need a graph of distance distance against time. Now, this is distance against time graph. On this graph, I can mark this position as an object is at top, and this is the position when object is at ground. Okay. So this is, just let me copy this thing first. And this is distance traveled. Distance traveled. Now, this time, I would like you to just take a screenshot right about now. Take a screenshot and the take a screenshot right now. And I would like you to give it a try. And then I will do it over here, and we can then compare our works with one another. The first graph will be distance and time. And listen, draw it on a fresh page so you can draw all the graphs in one single line from top to bottom. It's like in all of the graphs, the y-axis should be in the same line, like these graphs. You know how they are helpful? If all of the y-axis are in the same line and you have same time axis, all of the graphs are translating from one to another. So you can see that what was happening to distance, exactly what was happening to speed. So if you draw the graphs with all of the y-axis in the same line, you you have this advantage. So let's start. Draw the first graph of distance traveled against time. If you want me to check your work, you can send it to me in WhatsApp. Okay, if you're done with distance against time, now it is time to draw the graph of displacement. Displacement from the top of the building. And remember, we are considering upward direction as positive, because now we are dealing with vector quantity, so we have to decide about direction. So upward is positive. Anything that is downward will be negative. So then draw displacement time graph. Then we are drawing speed and time graph. Then we'll be making velocity and time graph. Okay, now let's pause the recording. Sorry. Now, uh, while going up, object has traveled less distance, and coming down, it has traveled equal distance. And listen, this is when the object is at the top. This is the top, and this is when it is back to the point of throw, because object has come back to the point of throw. Its displacement has become zero. Okay, when object comes back to this point where it has been thrown, the displacement should have become zero.
Yes.
Okay, because it is back to the point of throw. Displacement has to become zero, and afterward, object goes downward. It means its displacement is negative. So after that point, object's displacement increases, but because displacement is a vector quantity, when it increases in the opposite direction, we have to use an opposite sign for that. Speed. Object starts with a certain speed. The speed decreases at the rate of 10 meter per second square. At the top, the speed has to become zero, and then it increases at the same rate again. So object definitely hit the ground with more speed than it was thrown with. And this is because object is going up for a smaller amount of time, but it is falling down for a larger amount of time. So that's why this speed time graph should look like this. What about velocity time graph? Velocity time graph should look like this. And why is that? Because when object goes to the top and starts falling down, this is the top. And after this, direction of motion changes. This is moving upwards, and this one is moving downwards. And because of the direction of motion, direction of velocity changes. And when direction of velocity is opposite, it has to go with an opposite sign. That's why after the top, velocity becomes negative. What about acceleration? You should all know that the acceleration is produced by the gravity, and there is no change in gravity. And whether the object is going up or it is coming down, acceleration is always towards the surface of Earth, towards the center of Earth. So that means it is always downwards, and downward is considered as negative in this case. So acceleration all along will be minus 9.81 meter per second square. And it will stay 9.81 meter per second square all along. Whether object is coming down or going up or at the top or falling back, regardless of that, because there is only one force, there has to be only one acceleration. The other force, which can be air resistance, is completely ignored. Okay, so this is how all these things happen. Now, okay, this is a bouncing ball. Mechanics of bounce. So this object is falling down. This is impact, and then object goes up. Falling, rising, and in impact. So while this is happening, object is falling, kinetic energy is converting into, gravitational potential energy is converting into kinetic energy. And when this is happening, kinetic energy converts into gravitational potential energy. But what you cannot see with your normal eye is an impact. You just see this happening. This is what your normal eye sees. But if you use super slow camera, what you will find is that object okay, am I back online? Can you people hear me?
Yes.
Good, good. So see, this is an object that comes and hits the ground. This is the object that strikes the ground. And this is the object that leaves the ground. This will happen if we see in what? Super slow mo. And all this is happening during an impact. Okay. This is when object is falling. This is where the impact begins. This is where impact ends. And this is where the object is what? Rising again. Okay. This is what we normally cannot see with the eye. Okay? Let me show you this. Mm, not a bouncing ball, then I think this should help. Can you see it?
Yes.
Yes.
Okay. Tell me if you noticed. This is a golf ball. I hope you all have seen a golf ball or hold a golf ball in your hand. Have you?
Yes.
No.
Yes.
Now, a golf ball is, I think, as much I think it is the hardest ball I have seen. Like even the cricket ball is very hard, but it still has some soft cushion on the top with that leather and everything. But this is what a golf ball. It is not soft. Okay, but see, this is what I want you to see. Look, what has happened to the shape of the ball over there? Have you seen that the shape of the ball has gone a bit like ball has gone D-shaped or deformed? Hello.
Yes.
Okay, is my voice clear?
Yes.
Yes. Yes, sir.
Okay, listen. Uh, the ball gets deformed. So this is the time when kinetic energy of that uh, stick or whatever club, that kinetic energy becomes elastic potential energy of the ball, and the ball then goes forward with its own elastic potential energy, converting back to the kinetic energy. I can show you another example. This is a golf ball that has been a thrown onto a metal target with a speed of 200 miles per hour. And you cannot see these kind of things with your eye because these kind of things are happening at very slow rate. One last video and then we go. Okay, this is the one I was talking about. Now, this is slow motion. Look, the racket is about to hit the ball. Did you ever know that the ball goes through this?
No, sir.
Look, look. Did you ever know that the ball goes mm, like into this condition before it leaves the racket?
No.
No matter what impact we are talking about, this is what you have to understand, that whenever there is an impact, there is definitely a de-shaping taking place in the object that has that impact. Otherwise, objects do not start moving because object has to have that energy. And how does that object get that energy? By deforming itself. This is how the elastic potential energy goes into the second object, and then that object takes away with that elastic potential energy coming back to kinetic energy. See, the ball goes off with that kinetic energy, which is coming back to the ball. Okay. So similarly, when the ball has an impact with the ground, see, this is what I'm talking about. When ball hits the floor, do you see that D-shaping part over there?
Yes.
This is what you have to focus. Whenever there's an impact, there is a time when the ball has to go into that squishy, deforming situation. And then object starts coming back to the original shape. And this is when the kinetic energy again increases and the object goes back up. Okay. So this is where the impact begins. This is the time when kinetic energy of the ball is converting into elastic potential energy. Remember, this is the time when gravitational potential energy was converting into kinetic energy. Now, this is the time when elastic potential energy becomes kinetic energy again. And when object starts to rise, kinetic energy becomes gravitational potential energy. Now, how can we show all that on graph? So this is the physics of impact. And I hope you can understand that impact time is very, very small. Although a lot is happening over there, but this total time is very small. So be careful,
Okay, sir.
pay attention. This is the time when object is falling under normal gravitational acceleration. And believe me, this is the acceleration or this is the gradient of 10 meter per second square. But because I know I have to show a lot more acceleration than this, so I have to make this gradient look very small. Even this would not be according to the scale, but still it will be very close. Then speed reduces to 0, and then it increases in the opposite direction. And then this is happening. Yeah. This is acceleration equals to g downwards, impact acceleration is upwards. If ball is bouncing on the floor, then floor must be exerting force in the upward direction on the ball. So if force is exerted in upward direction, and remember, force and acceleration, they both have exact same direction. So if force is upward, it means acceleration is also upwards. So in this case, we are uh, showing that uh, downward direction is positive and upward direction is negative. So that's why downward gradient has positive value and upward gradient has negative value. And this is also acceleration equals to gravitational acceleration, and it is still downwards. That's why the speed will be decreasing in this case. Now, okay. How about acceleration? Now, there is a positive constant acceleration, then there is a negative constant acceleration, and then there is a positive constant acceleration. And the negative acceleration, which is the impact acceleration, is far more in magnitude than gravitational acceleration. So I hope you can still see that this is the time axis, this is the origin. So positive acceleration is a very smaller value. This is gravitational acceleration, G, and this is impact acceleration. So acceleration graph would show that, and remember, this is impact begins and impact ends. Now, and we are assuming that there is no loss of energy in the impact. Now, most weird graph now, speed and time graph. Speed and time. Now, again, constant acceleration. Okay, object is falling down, speed is increasing. When impact begins, kinetic energy starts to convert into elastic potential energy, speed decreases. Then when elastic potential energy starts coming back to kinetic energy, speed increases. And then when object starts to rise again, speed again decreases with the same acceleration as it was increasing. So this is the graph of speed against time. You, when you draw multiple impacts, will might be ignoring many of these curves over there. Okay. Tomorrow we will draw those graphs of multiple impacts. Okay. And I think this is it for today. See you people tomorrow.
Okay, sir. Allah Hafiz.
Okay.